guys, welcome to Learn Extra Live. Today is such a stunning Tuesday, perfectly for physical science grade 10s. Today we're going to get into some awesome stuff. I need you guys to fully focus, guys. This is going to be a special lesson. So you need to jump onto our Facebook page. That's facebook.com/Learn Extra, and our Twitter handle is @Learn Extra, guys. This is where you guys can ask questions on anything that you need to ask questions on. You can say hi, hey guys. You can talk to other mindsetters. You can chat to me and Tracy. Of course, that's what we're here for. We need you guys to fully be aware today because, guys, is this show not totally awesome? It is totally awesome. So you guys need to call your friends, your family, anyone you know that's doing grade 10 or anything actually, physical science. They need to jump onto the page. They need to start chatting to us, and we need to get moving and actually move everyone to be a mindsetter so that they too can pass. Guys, you don't want to be selfish and pass alone, right? So you need to jump onto the page and help other people pass. Hey, Tracy, how are you?
Very well, thanks so much. We are so excited to be getting into some physics. Grade 10s, we've been doing quite a bit of chemistry. We've been looking at atoms and the periodic table, and now what we're going to be doing is moving on with some physics. So it is transverse pulses and waves. Today we're going to be looking at a pulse and a transverse wave, and we're going to be considering similarities and differences, lots of key terminology. So it's going to be a great lesson.
Take it away, Tracy.
Thank you so much. We can get going. So grade 10s, this is what we're going to be covering today. We're going to be looking at how to define a pulse, and we will look at pulses specifically. We will consider the principle of superposition, and that's a key important one we're going to be using from now all the way through to grade 12. So important. We will also look at a transverse wave, and then discuss some terminology, some wave relationships, and lastly, always we spend some time looking at problems. So it's an important day that we've got planned. But before we get into it, I really want us to start with a demonstration. So Katlego, can you come help me?
For sure.
What we've got today is a slinky. And so hopefully we're going to have some fun with the slinky.
Awesome.
Let's join us on the floor as we put the slinky into action. Now, a slinky is basically a long coil, and I can play with it and send various different waves down it. So good fun, but there's lots of science that we can learn with a slinky as well. And so what I'm going to start with is just a transverse pulse. Okay, now I want you to watch this coil very closely because I'm going to send a wave down, or a pulse down, I should say, and that would be a pulse. Okay, I'll do that again. There we go.
That looks great.
A pulse is a single disturbance in a medium. So basically, I'm disturbing this medium, and the medium is the coil, and I'm causing that there to be a single disturbance. And notice it's reflected back. It's coming back to me, and actually in the opposite direction. It's inverted as it goes back. Now let me set up a wave, a transverse wave, all right? Now, what do you think the difference between a pulse and a wave would be? Well, a wave is a continuous motion, okay? So it's a repeated pattern of pulses. So let's go with a pulse, with a wave going. Okay, that's going to be a nice transverse wave. I'll stop it, and we'll go again. It's a repeated pattern of waves, of those individual. That was one individual pulse. Now if I repeat, it can go over again. And a transverse wave is quite different from what the other option would be, a longitudinal wave. Now I want you to notice that with a transverse wave, the particles, the individual coils, if I've got my finger on one or two of these, okay, go up and then go down. So for me it's going to the right and to the left, but for you, up and down, whereas the wave goes towards Katlego. So it's going across the floor. The individual coils are moving up and down at 90 degrees or at right angles to the direction of the wave. So let me go with those again. Notice the individual coils are going up and down, whereas the wave itself is going across. The other option is a longitudinal wave, and a longitudinal wave goes in the same direction the particles move in the same direction as the wave is moving. So I'm going to start a longitudinal wave. Watch closely as I do this to the coil. What do you notice? I'm moving the coils forward and backwards, and that is setting up this wave. Okay? Here the coils are moving in the same direction as the wave itself. So the coils are moving backward and forward, and the wave is going back and forward as well. They are parallel to one another. So let's turn to the board, and we'll get through quite a bit more. Katlego, thank you for your help.
Pleasure.
Brilliant. Let's turn across. We've done a bit on the slinky spring. I have got for you on the board here as well a simulation, and I want us to see if we can just formalize some of our ideas with a simulation. So I've got a pulse. Notice that pulse is the particles move up and down, and the wave moves across. If I go, let's try move it along, and I'm going to do it and hopefully press pause, and we can have a look at it a little bit. Notice for me here that the particles are actually moving up and down, and let's spot this green one. What do you think is going to happen to it when it's finished? Well, that green one is going to have to move back down once the wave has passed. So the particles of this medium are moving up and down. They are moving at 90 degrees as the wave, or the pulse in this case, is moving across. Okay, so a pulse, as we have here, this is a transverse pulse. The particles move up and down while the wave moves across. Let's formalize that a little bit more. The particles move at 90 degrees or at right angles to the direction of that the pulse is moving. Let's try and just formalize these. I've got quite a few words down that are key words that you need to understand. Okay, so we'll go through these in detail. I highly recommend, grade 10s, that you go and download these notes. I've done them for you. Download them and work through them and make sure that you've got these key definitions. Let's go through them individually. A pulse is a single disturbance which moves through a medium like a ripple in a puddle of water, okay? Just one single little ripple going along. Now, usually ripples come with lots of ripples, but we've just done a pulse, a single disturbance traveling through the medium. What is a medium, you ask? Well, it's a different word. A medium is the substance or material through which the pulse or the wave moves. So in this case, what we just had on the studio floor here was the coils as being the medium. The medium could be air if we talk about sound waves. The medium could be water if we're talking about water waves. There could be a number of different media, but when we speak of a medium, it's the substance that this wave is moving through, or this pulse is moving through. Okay? Let's go with a transverse pulse. So this was just an individual pulse, could be any pulse. Now we are specifically defining a transverse pulse where all the particles disturbed by the pulse move perpendicular, important word, which means at right angles, or even if you would like to add in there, at 90 degrees to the direction in which the pulse is moving. So the particles, I'll jump back to our picture here, the particles move up and down the way the pulse moves across. So they are going at 90 degrees to one another. Let's try and restart this, and I'm going to click on the pulse, and hopefully that you can see there. Now, I want to notice that this one's going out the window, okay? It's going on forever and ever. It's got no end. But what happens if I have a fixed end? So we'll restart it, and what do you notice? The pulse is reflected and almost inverted down. I'm going to once again pause that, and you can notice that those particles are not displaced forever. They get back. They are just moving up and down as this wave moves across. Let's jump back here and notice a few more keywords. Notice there are two different motions. Okay? Two different motions that we're talking about. The motion of the particles in the medium. And those particles remember I said are moving in this particular case up and down. Remember, as we said, they're going up and down. But the wave or the motion of the pulse, I'm going to add that in, moves to the left or to the right, depending on which way we're going. So there are two different motions, and that's probably one of the things that catches students out often, is they're thinking, which one am I talking about? Well, if you're talking about the wave or the pulse, you're talking about the whole motion. If you're talking about the particles, they are just moving up and down for a transverse pulse or a transverse wave. Let's go across to some more important words. The amplitude, this is a lovely one, and it comes up with pulses and waves, which we'll discuss in a moment, is a measurement of how far the medium is displaced momentarily from its position of rest. Now I'm going to go back to my little animation, and we'll go back to a pulse, and I'm going to choose that no end. We'll restart it, okay? And what I want to do here is I want to drop this amplitude right down to 22. What do you notice? That amplitude is very small, very, very small. Whereas let's shift this amplitude up. Let's take it up to 70 odd, okay? And I'm going to restart. And now the amplitude is big. The amplitude is the height above the rest position, okay? Now, as we go through, we're talking about that distance away from the rest position. The rest position would be the position if there was no disturbance, okay? The rest position, sometimes called the equilibrium position, okay? So we'll go back to our definition. The amplitude of a pulse is the measurement of how far the medium is displaced or moved away, momentarily away from its position of rest. The pulse length is another nice one. We speak about is a measurement of how long the pulse is. So how long this disturbance is. And I've got a picture here on the board for you. Sorry, let's just shift that up slightly, of these two. The pulse length would be this distance that the disturbance is, how long the disturbance is, whereas the amplitude is the maximum height that the medium is displaced away from rest. Now watch out for the word height, because we do sometimes speak about the height of the wave from crest to trough, so watch out for that. We'll talk about that in the next segment. But what I want you to notice here is that this A is from its rest position to its highest point. Okay, so it's the distance that the substance is momentarily displaced. Well, what happens now when we've got two pulses and they're coming together? What's going to happen when they meet? Well, that is talked about when we speak about the principle of superposition. And superposition is basically saying when you've got two disturbances and they're coming together and they occupy the same space at the same time, i.e., they're going to be on top of each other, what's going to happen? Well, you would have to take the sum of the two disturbances. And we can either have constructive interference or destructive interference. Constructive interference would build up, okay? Whereas destructive interference, those two waves or two pulses would start to cancel each other out. So let's discuss each of those, and I've got some pictures here for you. If you've got two waves, and I'm talking about the left-hand side of this picture for the start, two waves move towards each other, or pulses move towards each other. Notice that these are in the positive y-axis. They move to each other, and notice at this point here, they're in the same place at the same time. Okay, what happens to them? Well, they both are positive values, so they add together to make one big pulse. Okay, and that would happen momentarily, just for an instant. And then once they are now past each other, or they've interacted, they would move past each other, and no longer they would carry on going and move away from one another without any further interference. Now, students often ask, well, that's quite easy if you look at it in the positive direction. But what happens if you're working with a pulse that is in the negative y direction? It can happen, and that would work perfectly fine as well. So notice I've got these two that are little dips or troughs. They constructively interfere because they're going in the same direction, and so we make one big pulse, and then they move away from one another. Constructive interference, we'll finish off with this, takes place when two pulses meet each other to create, and I want you to get this, a larger pulse. The amplitude would be the sum of the amplitudes of the two initial pulses, and this could be two crests meeting, or two positive in the positive y direction, or two troughs meeting. So think about constructive interference, and we're going to come back and we'll finish off with destructive interference. Katlego.
Thank you, Tracy. So guys, we deserve a little bit of a break, but during this break, I need you guys to check out our site, guys. This is the site that has the notes, it has schedules, it has videos, and I've also posted a fast link for you guys on our Facebook page that will take you directly to the grade 10 notes that Tracy is currently using. I know, that's awesome, right? You guys really need to check it out, guys. Download the notes. Anything that you need to do, just have them in front of you, and we'll be back right after this short break. Hello guys, welcome back. We are doing physical science today, guys. Grade 10s, I hope that you've so far had a great show and you are just stuck to those seats because it is really awesome. I want to tell you guys that if you jump onto our learnextra.co.za/lives, you'll see we have notes and you'll see we have videos, guys. If you click on that video, it has a direct link to YouTube, but I can also tell you where you can find our YouTube videos. That is youtube.com/mindsetlearn, guys. Please save that, guys. I'll write it on the page just now, just to remind you guys. But you guys need to check out our videos in case you missed a show. I know most of you are like, oh man, I missed last week's physical science. Don't you worry, we've got your back. Just jump onto that page, guys, and you'll have all that you need to have, guys. We will never leave you in the dark. Don't you dare worry. Don't worry. We are here for you. Over to you, Tracy.
Thanks, Katlego. We're ready to start grade 10s. We're going to carry on with the idea of the principle of superposition. And remember, we said if two waves are or pulses are coming towards one another, they are in the same place at the same time, they can either constructively interfere or destructively interfere. So let's have a look at destructive interference and what we mean by that. Destructive interference takes place when two pulses meet and the result is a smaller wave or a smaller amplitude disturbance. The amplitude, remember, that is the displacement away from the rest position. The amplitude is going to be how much it's been displaced away from its original rest position. The amplitude of the resulting pulse, again, is a sum of the amplitudes of the two pulses, but one value will be a negative number. So let's have a look at what I mean by this. Well, if you imagine two pulses coming towards each other, and I'm just going to give these some values. Okay, so I'm saying that pulse is 2 centimeters up, and that pulse is 2 centimeters going down. When they come together, what is the result going to be? Well, 2 centimeters up and 2 centimeters down will cancel each other out. And so if you notice, for that instant, we have here a straight line where the positive pulse has been put as a little dotted line and the negative pulse is a dotted line to indicate to you that they are there, but the effects of them have cancelled out. And then notice the waves move past one another and carry on undisturbed. Now, this example was one where those two values were exactly the same. I'm going to just put a positive there and a negative there to indicate that they're going in the opposite direction. But what happens if they don't perfectly cancel? Well, I've got a picture of that as well. We've got a positive pulse here in the positive direction, and we've got a little negative. Notice this negative. Sorry, my line is a bit squiggly. We've got a negative there going, but as a much smaller value, okay? And as those two meet in the middle, they interfere, but they don't cancel out completely. The one is positive, the one is negative, but the positive one is quite a lot bigger than the negative one. You are just working with the difference between them. And you would get a small pulse for that instant, and then notice as they move apart, they would continue to move away from each other undisturbed. So remember, the principle of superposition is that those two pulses are at the same point in time, and they would add together or cancel each other out if it was destructive interference. Let's continue with our understanding of transverse waves. We've spoken about transverse pulses, and a pulse is a single disturbance in the medium. Okay, whereas a wave is going to be a periodic, continuous disturbance that consists of a train of pulses, so lots of pulses going at the same time. And I want us to jump across. I've started a new set of pulses going, but this is a continuous set of pulses. So notice that's going to be us starting us off, and let's just restart that, and we'll watch as those particles get moved up and down. Okay. Now, I'm going to turn it to manual, and let's just slide this down to our start point and shift that up and down. Okay. Now, notice those particles are not actually moving out the window. They look like they are, but the particles themselves are still attached on this edge. So they are actually just moving up and down, and I'll go back to oscillate, and we'll pause it there. Those particles are shifted up and down. And let's watch this green one. I'm going to let it go in a moment. Okay. Let's try and go through a step by step. I'm going to go across here. I want you to look at the green one and notice it is just going up and down. So it is itself not moving across the page, it's just going up and down on the page, whereas the wave is moving continuously in this set in towards the right. Let's continue with our notes, make sure we've got everything. A transverse wave, and I know someone on the page asked this a few moments ago. So what is a wave? A transverse wave is where the movement of the particles of the medium is perpendicular, i.e. at right angles, or if you prefer 90 degrees, to the direction of the propagation of the wave. Now, to propagate is to continue to pass on. So the wave is moving across, whereas the particles are moving up and down. Note, there is no net displacement of the particles on the medium. Net means overall. So there's no overall displacement. Those particles aren't suddenly jumping to somewhere else. Okay? They are moving up and down, but the wave that moves across. So I've noted there, the particles move up and down and return to their equilibrium position. But there is a net displacement of the wave. The wave moves across, the particles just moving up and down. Let's go through a few more words. A crest is one you'll come across often. Is a point on the wave where the displacement is at its maximum. So let's just find one there. This would be termed a crest, if you can see that highest point on the wave. By contrast, what do you think the bottom one would be called? The maximum displacement below the rest position. That would be called a trough. Going down, a crest and a trough. So a trough is going to be the point in the wave where the displacement is at a minimum. So that's its lowest point. The amplitude, we talked about amplitude when we just discussed pulses a little while ago. And a pulse was just a single disturbance. The amplitude of a wave is the maximum disturbance or displacement of the medium from the equilibrium or rest position. And students often get this confused. Okay? When we're speaking about the amplitude, we are speaking about it from rest to the top or from rest to the bottom, not from the right to the bottom all the way to the top. be careful of that. The wavelength of a wave is the distance of one complete wave, measured between any two adjacent points that are in phase. So any 2 points that you can say that is one complete wave. I want to jump across and let's just talk about these for a bit. If I was to, I'm just going to step that through. Okay, this is the start of my wave, and I should have actually been one step back, and I can't go back, but that would be one complete wave from start to finish. From start to finish. Or I could say maybe my start point is from my highest point down the dip to my next highest point. Okay, that would also be one complete wave. Or another one, I could go from my lowest point up and down to my lowest point again. So it could be between, it's just simply the distance of one complete wave. And students often get confused with that. So a wavelength is the distance of one complete wave measured by any two adjacent points that are in phase. And the symbol that we give it is this interesting new little symbol, lambda. Okay, you probably have not come across it before. It's a Greek letter, lambda, and it is measured in meters. Okay. Let's go across, and I've got a question on the next page for you that just will define those two. Consider the diagram below and answer the questions. The amplitude of the wave is shown by letter what? Well, amplitude is the distance away from the rest position. So let's have a look and find it. Is it going to be A or is it going to be B? Well, lots of students will probably pick A. But think about it. That is from the minimum to the maximum. So it's not from the rest position to its maximum. The correct answer here is it is B, the amplitude of the wave. If I gave you A, and I said to you, and I gave you A as being 4 meters high, what would B have to be? What would, if I gave you the full height of the wave, what would the amplitude be? Well, it would have to be half of that. So this would have to be 2 meters. And your teacher might do that in asking a question to you. They could give you the full height and ask you what the amplitude would be. Let's go to the next one. The wavelength of a wave is shown by the letter. Well, it is the distance of one complete wave. So C, no, it can't be, but it can be from the trough up down to the next trough. That would be D, the wavelength. Now that we need to come across to a few more important terms, the period and the frequency. And these can be confusing, so work with me very closely here. The period is the time taken for one complete wave to pass. Okay? So what I would do is I would hold my stopwatch and say, 1 wave, stopwatch off. Now obviously, if you were measuring with a stopwatch just 1 wave and it's going really quickly, then we might have serious issues with human error and my reaction times. But the period is the length of time it would take for 1 wave to pass. The symbol is given by the letter T, and it's measured in seconds. The frequency is the number of waves passing a given point in 1 second. So now I say, okay, I'm going to time 1 second. You count how many waves go past. Okay? The difference is that these things are the inverses of one another. Frequency is how many waves go in 1 second. The period says how long does it take for 1 wave to pass. And that is a key those two are key definitions that you need to make sure that you work through. The symbol for frequency is just the little letter F. It is measured in hertz. And notice I said to you that these two are inverses of one another. And I've got an equation here, I'm going to rewrite it. Frequency is equal to 1 divided by the period, because they are by definition inverses of one another, the frequency is how many waves go past in 1 second. The period is how long does it take for one wave to pass. So we've got a nice equation there to work with. Then, to add to that, we will probably work with the speed of a wave. And speed is quite a nice calculation to do. And I've got some questions on the speed of a wave for you in a few moments. But I want us to talk about the speed. Now, if you were driving a car, you would be maybe driving in kilometers per hour, okay? It's always, when we speak about speed, meters per second or kilometers per hour. It is a distance divided by a time value. So let's do the same for waves. Well, it is the distance traveled divided by the time taken. I have got a value, or a name, I should say, not a value, for the distance of one wave. And that value is going to be lambda, okay, which is one wavelength. Okay, the distance of one wave. And I can divide that by the time taken. Now I have a symbol for the time taken, a value for the time taken would be the period, the time it would take for one wave to pass. And that we call the period. So, if I take this further, a little bit far, okay, for the speed of the wave, I could write this, and follow with your maths with me, as lambda multiplied by, not divided by, but multiplied by 1 over the period. So I've just taken that to the side and saying I'm multiplying by 1 over the period. That means that I could write lambda, and what is this part? 1 over the period. I can zoot back. We have an equation for that. Frequency is 1 over the period. So I can simplify this whole equation by saying is the speed of a wave as given by v is equal to lambda multiplied by the frequency of the wave. The lambda being the wavelength. And when we come back from this next break, we're going to talk through lots of questions so that you can get some practice. Over to you, Katlego.
Thank you, Tracy. So you heard Tracy, you need to make it back right on time after this break. Maybe stand up, stretch your legs, but be sure to join us as soon as we come back. See you just now. Welcome back, Mindsetters. As you know, we are doing physical science, and what an awesome show it has been, guys. If you have been on the page lately, around about now, I hope you have, because other than that, I mean, what else would you do? You need to jump on the page. I've posted all the sites that you guys need to jump onto to check out notes and schedules, to check out YouTube videos, to check out anything, guys. Just jump on it. Even the FET websites that Tracy was using right now, I have posted that on the page, so you guys can just click on that link and it will take you directly to that, and you can play with those slinky dinky waves and have a bit of fun, show your little brother and your little sister, because guys, this is really going to help you learn. It's so nice when you see things in color and they come alive, so make sure that you are checking that out right now. Over to you, Tracy.
Thanks, Katlego. Grade 10s, we're going to carry on with waves and pulses and look at some questions that you could be asked. So, across to the board. Question 1. When a particular string is vibrated at a frequency, vibrated would be to move it up and down, is vibrated at a frequency of 10 hertz, a transverse wave, okay, some key words here, a transverse wave of wavelength 0.25 meters is produced. Determine the speed of the wave. Now, I want us to write a list. Whenever you get a question like this, write a list of the values you have. So let's go across and write the frequency is equal to 10 hertz. The wavelength would be lambda. That's not an X, that's a little lambda. Is equal to 0.25 meters, and they ask us to calculate the speed. I always write that type of a list because it helps me to interpret what's happening in the question. Okay, so you've got a list of values, and you can say, what equation should I use to tackle this? And maybe you've got a data sheet, and you can go across to that, and you find your equation. V is equal to frequency multiplied by lambda, and we can plug in our numbers. 10 multiplied by 0.25, put them in brackets to help indicate that we're substituting those. And you could possibly go across to your calculator. 10 multiplied by 0.25. Well, I know if I'm multiplying by 10, I can just actually move that decimal place across. So it's going to be 2.5 meters per second. And do we know a direction for this? We don't, so in the positive direction, if you were required to give a direction. Let's move across to the next one. Here we've got a fly. Flaps its wings back and forth 200 times each second. Now the each second bit is important. 200 times each second means that if I was timing 1 second, and you could count that fast, it would be going 200 times. So what value is that 200? Remember I said write a list. It has to be the frequency is 200 times per second, or 200 hertz. Okay, by definition, and we had this equation earlier, frequency is equal to 1 over the period. If we were to work out the units for frequency, it would be 1 divided by seconds. Okay, this is just units. So 1 hertz is actually 1 over 1 second. Okay, if I just clear this so that we can carry on with our discussion. Okay, we had 200 hertz. The question was, calculate the period of a wing flap. How long each wing flap would be for that little fly. And so I had the equation, frequency is 1 over the period. I want to work out the period. So I need to move that across, rearrange this equation. Well, you're going to take the period up to the other side, and because it was dividing on the right, when we take it across the equal sign, it becomes multiplying. And when we take that one across, it's going to be period is 1 over the frequency. So the period is going to be 1 divided by 200. And you can punch it in your calculator. 1 divided by 200 equals, and we're going to say 5 times 10 to the negative 3 would help me. So we've got the period, the period t is equal to 5 times 10 to the power of negative 3. What is the unit? Well, it's a time value, so the unit is in seconds, and that is my final answer. Let's jump to the next question. Here we have a whole number of questions based on question 3, so follow with me closely. Water waves crash against a seawall around the harbor. 8 waves, and that's important, 8 waves hit the seawall in 5 seconds. The distance between successive troughs is 9 meters. So there they've got it on the diagram. Between C and the next trough going across is a distance of 9 meters. The height of the waveform, trough to crest. Okay, now I'm going to add that in on my picture because it's not given, is 1.5 meters. Because they're telling me its trough all the way through to a crest is 1.5 meters. Now I've drawn along this diagram, but I want us to count quickly how many complete waves are indicated in the sketch. Complete waves would be going start to finish. Now, this is tricky. Follow it closely, okay? I'm going to draw and stop. I'll draw it in pink across the page. That's going to be the high point, the low point, back to midpoint. That's 1. I'll change colors. From midpoint, high point, low point, midpoint. That's 2. I'll change colors. Let's go with green. High to the low, back to the midpoint. How many complete waves have I got? We have 3 complete waves. We've got the purple one, the blue one, and then the green one. So 3 complete waves are indicated in the sketch. Next question. We've got the same diagram. Write down the letters that indicate any 2 points that are in phase. Now, in phase means that they're at the same point and they're going to be moving in the same direction. So let's have a look. We've got lots of points here. I'm going to pick one here. D, that point there would be moving downwards. So B and D going to be going downwards. So those 2 points, B and D, are in phase. What about some more? C and E, they're at the lowest point and it's going to be moving up again. Lowest point going to be moving up again. So C and E will be points in phase. And there are quite a few on this diagram, so you could pick any 2 points. What are points that are out of phase? Well, you could go and find them. C and D would be out of phase. E and F would be out of phase. G and H would be out of phase. There are quite a number. It doesn't really matter which ones you choose as long as they are out of phase. And out of phase would mean not at the same point and not going in the same direction thereafter. Now, I know those points are actually just moving up and down, but the wave that follows would move in whatever direction. Write down the letters that indicate that points that are able to represent 1 wavelength. Now, for that, I'm going to go back to my previous diagram because I drew over this quite a lot. And what it would be if we were to choose, and I think let's go back to our diagram we're using here. Notice that this point would be from C to E would be 1 whole wave. Another one, B all the way up to D, would be 1 complete wave. So we've got quite a number here that could represent the length of 1 wave. The distance between B to D would represent 1 wave. From C to E also represented 1 wave. From D to F, we could choose another one. D up, down, through to F would also represent 1 wave. So we've got quite a couple here we could choose from. Calculate now the amplitude of the wave. And they have given us in the diagram, actually they gave it to us in the text, that the height of the waveform from trough to crest is 1.5 meters. So here we've got it from the trough, the lowest point, through to the crest, the highest point. That is a distance of 1.5 meters. You've got to ask yourself, is that the answer? And the answer is no, it's not. That is the lowest point to the highest point. What is our definition of amplitude? It is from the rest point or the midpoint, that it would be from the midpoint to the highest point or the midpoint to the lowest point. So what is our answer going to be? It would have to be 1.5 divided by 2, which would be the half of that, okay? Because 1.5 divided by 2, I believe, is 0.75. We can go and check it if you wanted to. Let's clear that. 1.5 divided by 2, and it's 3/4 or 0.75, which means that this value, and I would need to give a unit in meters, is actually just the top part or just the bottom part. It is the amplitude, the distance from the rest position, okay, from the equilibrium point. Let's continue. Remember I said we've got lots of sub-questions to this. Show that the period of a wave is that value. Okay, now you cannot use that value in your answer. You've just got to prove it's that value. Okay, so your final answer should be that t is equal to 0.625 seconds. How do you do that? Well, let's have a look at what we've got. The water waves crash against the seawall in the harbor. 8 waves hit the seawall in 5 seconds. This is going to be what I will use, okay? Because what does that tell me? That's telling me how many waves go past in 5 seconds. Well, let me use that. 8 waves go past in 5 seconds. So, what about in 1 second? Okay, so I'm going to take that value and say, in 1 second, how many waves? Well, I'm going to be able to go 8. Let's just clear this slightly. I'm going to go 8 in 5 seconds. How many in 1 second? Well, it would be 8 divided by the 5. It would be how many waves go past in 1 second. And that's going to take me to a frequency value. And we'll jump to our calculator. Let's clear that. 8 divided by 5. And you're going to get 1.6. So frequency is 1.6 hertz. Okay. And then we're going to do in our next step, the period is 1 over the frequency, because the frequency was 1 over period. Period must be 1 over frequency. And so 1 divided by 1.6. Let's do that again. 1 divided by 1.6. And you get the answer, 0.6. That was 0.625 seconds was the value for the period. And all these types of questions really build on your knowledge. But if you don't know what the definitions are of all these words, period, frequency, amplitude, you're not going to be able to answer the question. So make sure that you go back, grade 10s, go and print those notes, go and make sure that you've got all those definitions right up your list and study these very well. Because without the definitions, you're not going to be able to answer the questions. Katlego, over to you.
Thank you, Tracy. I think we have a question, actually. Let me just find it, sorry. So
I think I might have another question here.
Okay, do you want to... Wait, let me just clarify, please, for Michelle. She was asking about in phase and out of phase. I know you covered that, but can you please just put it all in a bundle?
I can. Michelle. I hope you're listening, Michelle. So when we speak about values that are in phase, we're saying that those points are at similar points, if you like, on the wave. So if my fingers are going to be the points on the wave, they're both at crests, okay? And they're both going to go into the dip phase, so into the dip. So what you are looking for when you're looking at points in phase is you're looking at points that are going to undergo this, are undergoing similar motion, okay? Whereas points that are out of phase would if you had them in superposition, as in if they were in the same place at the same time, they would cancel out. And that's how it's relating. So points that are in phase, if they were to add together, they would make a higher one. That's what we spoke about with constructive interference. Whereas points that are out of phase would be one going into a dip, one going into a crest. And so what's going to happen is that they will cancel out when they meet. Or if they were to meet. So points in phase would, if they were to meet, constructively interfere. They are at the same or similar points on a wave, whereas destructive interference would occur if you've got points out of phase.
Awesome.
Let's look at this last question, and I think I've actually already answered it. We looked at the frequency, they're now asking us the frequency of the wave, and I actually answered that. I think it was 1.6 hertz. When we did the previous question. So there probably are multiple ways of answering the same type of question, and you just need to make sure that you go back and that you look at your definitions. Grade 10s, it's wonderful to make sure that you're learning so much, and I hope that this has really been a helpful session.
Thank you very much, Tracy. I think it has really been really helpful. It shows that you guys are understanding so much more. And I want to urge you guys to actually help each other on the page. I've already seen here that Lerato asked a question and Tabang kindly answered it for her. Tabang, well done, and Lerato, well done for asking as well. Guys, keep helping each other, keep learning more and keep learning extra. And please, same time, same place, you need to be joining us, guys, because this is the most awesome place that you can be on a Tuesday afternoon. Thanks for an awesome show, guys. Bye-bye.
Transverse wave, and then discuss some terminology, some wave relationships, and lastly, always we spend some time looking at problems. So it's an important day that we've got planned. But before we get into it, I really want us to start with a demonstration. So Katleho, can you come help me?
For sure.
What we've got today is a slinky, and so hopefully we're going to have some fun with the slinky.
Awesome.
Let's join us on the floor as we put the slinky into action. Now, a slinky is basically a long coil, and I can play with it and send various different waves down it. So good fun, but there's lots of science that we can learn with a slinky as well. And so what I'm going to start with is just a transverse pulse. Okay, now I want you to watch this coil very closely because I'm going to send a wave down, or a pulse down, I should say, and that would be a pulse. Okay, I'll do that again. There we go.
That looks great.
A pulse is a single disturbance in a medium. So basically, I'm
Hello guys, welcome to Learn Extra Live. Today is such a stunning Tuesday, perfectly for physical science grade 10s. Today we're going to get into some awesome stuff. I need you guys to fully focus, guys. This is going to be a special lesson. So you need to jump onto our Facebook page. That's facebook.com/Learn Extra, and our Twitter handle is @Learn Extra, guys. This is where you guys can ask questions on anything that you need to ask questions on. You can say hi, hey guys. You can talk to other mindsetters. You can chat to me and Tracy. Of course, that's what we're here for. We need you guys to fully be aware today because, guys, is this show not totally awesome? It is totally awesome. So you guys need to call your friends, your family, anyone you know that's doing grade 10 or anything actually, physical science.
So for me it's going to the right and to the left, but for you up and down, whereas the wave goes towards Katleho. So it's going across the floor. The individual coils are moving up and down at 90 degrees or at right angles to the direction of the wave. So let me go with those again. Notice the individual coils are going up and down, whereas the wave itself is going across. The other option is a longitudinal wave, and a longitudinal wave goes in the same direction. The particles move in the same direction as the wave is moving. So I'm going to start a longitudinal wave. Watch closely as I do this to the coil. What do you notice? I'm moving the coils forward and backwards, and that is setting up this wave. Okay? Here the coils are moving in the same direction as disturbing this medium, and the medium is the coil, and I'm causing that there to be a single disturbance, and notice it's reflected back. It's coming back to me, and actually in the opposite direction. It's inverted as it goes back. Now let me set up a wave, a transverse wave, all right? Now what do you think the difference between a pulse and a wave would be? Well, a wave is a continuous motion, okay? So it's a repeated pattern of pulses. So let's go with a pulse, with a wave going. Okay, that's going to be a nice transverse wave. I'll stop it and we'll go again. It's a repeated pattern of waves of those individual. That was one individual pulse. Now if I repeat, it can go over again. And a transverse wave is quite different from what the other option would be, a longitudinal wave. Now, I want you to notice that with a transverse wave, the particles, the individual coils, if I've got my finger on one or two of these, okay, go up and then go down. So
They need to jump onto the page, they need to start chatting to us, and we need to get moving and actually move everyone to be a mindsetter so that they too can pass. Guys, you don't want to be selfish and pass alone, right? So you need to jump onto the page and help other people pass. Hey, Tracy, how are you?
very well, thanks so much. We are so excited to be getting into some physics. Grade 10s, we've been doing quite a bit of chemistry. We've been looking at atoms and the periodic table. And now what we're going to be doing is moving on with some physics. So it is transverse pulses and waves. Today we're going to be looking at a pulse and a transverse wave, and we're going to be considering similarities and differences, lots of key terminology. So it's going to be a great lesson.
Take it away, Tracy.
Thank you so much. We can get going. So grade 10, this is what we're going to be covering today. We're going to be looking at how to define a pulse, and we will look at pulses specifically. We will consider the principle of superposition, and that's a key important one we're going to be using from now all the way through to grade 12. So important. We will also look at a